divided in three fundamental steps. First, we need to model the system of interest in a formal way. Then we need to specify the property of interest in a formal language. And the third step is to check whether the model satisfies the property of interest. For the modeling part, we can use classic labeled transition systems like cryptic structures, in which we have a set of states, a set of transitions, and for every state, we have the atomic propositions that are true on it. Atomic propositions are classic Boolean variables. For the specification part, generally, in model checking, temporal logics are used because they give the ability to represent the time without using the time explicitly. And there are two main categories of temporal logics, linear and branching. In linear, the idea is that the computation is totally ordered, so we have only one possible successor, and we want to verify properties over the time, like next, so in the next step, eventually, so at certain point we want to verify the property of interest, or globally we want to verify that in every state of our computation the property holds. The other category is on branching, temporal logics, and one of them is CTL, in which instead we have as a structure a tree, so that represents all the possible computation of our system. And we want, for example, to check whether for all paths we can verify a temporal property, or there exists a path in which we can verify the property of interest. So given the formal model of our system, like a cryptic structure, and a specification in terms of temporal logics, we can verify whether the model satisfies or not the property of interest. That is the third step. This technique has been introduced in the 80s, and after has been extended to multi-agent systems to represent distributed and intelligent systems that interact with each other. So in this context, we have several agents. Each agent has a set of strategies. A strategy is a conditional plan that prescribes for each action, for each situation, an action. And given a strategy for each agent involved in the mass, we have a strategy profile, and we can determine the unique computation that is in accordance with these strategies. For the modeling part, we need to extend classic cryptic structures with a set of agents and a set of actions. And with respect to the interaction between the agents, we have different transition functions. The two main categories are turn-based and concurrent. In the turn-based setting, in every state we have an owner, and only the owner of that state determines the next state in our mass. While in the concurrent setting, every agent needs to select an action, and given a table of actions, one for each agent involved in the mass, we can determine the next state in our system. In multi-agent systems, we have also additional features like the concept of the strategy, and with respect to the memory of the strategies, we have different classes like memoryless, in which we take into account only the current state to determine the action, and memory-full strategies in which we consider the full history of the mass to determine the next action. To well understand the whole machinery, we can consider a simple example, paper, rock, and scissors, in which we have two agents, Alice and Bob, and the three related actions. Then we can define this game as a one-shot game starting from the initial state, Si, and the three possible successor states that determines the outcome of the game. We can define two atomic propositions for the winner, and we need to consider all the possible couple of actions for the agents. So if both selects the same action, so we have a tie game, while in the other cases, we can follow the classic rules of the game and determine the winner. In model checking, we consider the verification over infinite traces. So for completeness, we need to add loops. The stars means no matter what the agent does. And we can select, for example, a strategy for Alice for in every history paper, and for every history for Bob, we can select Rock. Given these two strategies, one for each agent involved in the system, we can determine the unique computation in which Alice wins. Another important feature in multi-agent systems is the visibility. And in particular, we can distinguish between two main categories: perfect information mass, in which in every state and in every situation, each agent has full visibility about the current state and the mass model, and in the imperfect information setting, in which there are some situations in which some agents cannot distinguish the current state with respect to a subset of mass states. This is related to the modeling part. We can move to the specification part, and in particular, we need to extend classic temporal logics to logics for the strategic reasoning, like alternating time temporal logic, that is an extension of CTL, in which instead of having path quantifiers, there exists a path or for all paths, we have strategic operators over coalition of agents that tell us if there exists a strategy for a coalition A to achieve a strategic objective. So in this logic, the strategies are implicit because we quantify over coalitions. To well understand this logic, we can consider a simple example in which we have two agents, alpha and beta, and then a temporal objective, globally not fail. So given this specification, we can check whether the coalition alpha and beta have a strategy to guarantee that the system can prevent the failure in every state. Given the specification part, then we have the third step of the verification process, that is the solution of the model checking problem, and the key point in the verification is the complexity of the verification approach. And for ATL, the two parameters that have an impact on the model checking complexity are the visibility of the agents and the memory of the strategies. In particular, for the perfect information setting, we have for both memoryless and memoryful strategies a polynomial time algorithm that is a classic fixed point characterization. It's an extension of CTL. While if we move to the imperfect information setting, the problem becomes in the polynomial hierarchy P and P. So the idea is that we have an oracle that guesses a strategy, and then we have a polynomial time algorithm for the memoryless setting, and it is undecidable in general for the imperfect information and memoryful setting. For the extension of ATL star, in which the strategic operators and the temporal operators are not coupled, so we have the same relation as CTL star and CTL, the problem becomes P space for memoryless in both perfect and imperfect information, while for perfect and memoryful strategies is 2xp time complete. To solve this model checking approach, we need to use automata, 3 automata, and the 2xp time complexity is related to the size of the formula, but the bottleneck in general is the size of the model, so is still tractable, while it is undecidable for imperfect information and memoryful strategies. There is also another logic for the strategic reasoning that is called the strategy logic, in which we can treat strategies as first-order objects, so we can quantify over strategy variables and check whether there exists a strategy or for all strategies. To link strategy variables to agents, we have an additional operator, the binding operator, that gives us the ability to link the current strategy variable with an agent. And we can also share the same strategy with different agents. Thanks to this logic, we can represent several solution concepts fundamental in game theory, like the Nash equilibrium. well understand the difference between ATL and strategy logic, we can assume the same property of interest in which, as you can see, the temporal part is the same as we have defined for ATL. The difference is in the quantification part in which we need to make explicit also the opponents. The opponents are the universal agents, while for the coalition of agents that wants to achieve the temporal objective, we have the existential quantifiers. For the verification part, since strategy logic is more expressive of ATL, we cannot have good results. For example, for memoryless, we have again p-space complexity as for ATL star, and for the perfect information and memoryful strategies, the problem is non-elementary. Non-elementary means that we have a tower of exponential, and the tower is a parameter of the problem, and in particular, the parameter is the number of alternation between existential and universal quantifiers. And again, for the imperfect information and memoryful setting, the problem is undecidable. Given the relevance of this logic, several fragments have been introduced, like strategy logic one goal that has a 2xp time complexity, like ATL star, but it is more expressive, and also strategy logic simple goal in which we have a model checking complexity that is polynomial, because we can use again a fixed point characterization. To conclude the introduction, I would like to emphasize the difference and the relevance of logics for the strategic reasoning with respect to temporal logic ones. And to well understand the difference, we can consider a simple example of two agents, two vehicles. The vehicle B is in front of A, and the goal is that A wants to pass B. We can assume that we have two actions for both the agents, and in particular, A can do the actions pass and not pass, and the agent B can select accelerate and not accelerate. Given this context, we can generate a formal model in which we need to consider all the possible combinations of actions, and in particular, also in this case, we can assume a one-shot game that, starting from the initial state, assume every possible couple of actions. Our goal can be defined with the atomic proposition G, and it is satisfied only if the first agent select pass and the second one not accelerate. Given this model, to verify properties, we need to do the unwinding, that is a tree that considers all the possible successors for every state. In this context, the unwinding is simple because after the first step, we will remain always in the same state. However, this is important to project the verification of the temporal and the strategic logic formulas. In particular, for the formula exists eventually G, that is in the CTL logic. So we want to check whether there exists a path in which sooner or later we can verify the atomic proposition G. This property is true because we have a path starting from the initial state that verifies such a formula. However, we cannot verify the property there exists a strategy for the agent A such that we can achieve the atomic proposition G. This is because if we select the strategy P for the agent I, we need to consider all the possible opponents' actions, and in particular, in this case, the agent B can select accelerate, and we cannot verify the property of interest. So in conclusion, given the property of interest in terms of temporal property, we can verify the CTL counterpart, but we cannot verify the related property on ATL. So the main difference between temporal logics and strategic logics is the fact that we can verify properties over subsets of paths. While in CTL, we can only verify if there exists a path, or for all paths, we can verify the property of interest.
So, excuse me, is the problem here that, so you can see that it's possible that A can pass B, but only if B is playing really stupidly, right?
Yeah,
So this is the sense, right?
Yeah, this is the key point. And in fact, to verify the property, we can add in the strategic operator also the agent B. So B can cooperate, and in that case, we can achieve the temporal objective.
Yeah, exactly. Okay, thank you.
So we can move to some of our main results. I have divided them related to the modeling, specification, and verification part. For the modeling part, we have introduced a new notion of strategies that we call natural strategies to represent the human's point of view in a multi-agent setting. The idea is that we have an ordered list of condition actions rules instead of having a function. And the condition depends on the memory of the agent, and in particular, if it is memoryless, the condition is a Boolean formula that needs to be verified in the current state. If it is verified, then the agent can apply the related action. For the context with the memory, the idea is to use regular expressions in which every state, again, is defined over Boolean formulas. To guarantee that at least one action is available in every state, we assume that the last couple in this list is true idle. In this way, at least the idle action is available for every agent in every state. Again, it's an ordered list, so the first condition that is true in the current state determines the action of the agent. Given this new representation for the strategies, we have also defined the complexity of these strategies, since we are talking about bounded rationality, and we have defined the three notions of complexity related to the number of used atomic propositions in every condition of our natural strategy, or by considering the largest condition. So we take into account only the condition that has the maximum number of symbols. And the last one is the total set of the representation. We count every symbol in every condition of the natural strategy, and in this way we determine its complexity. To well understand the notion of natural strategies and their complexity, we can consider a simple example to purchase a ticket in which we have three condition actions rules. So in every state, we need to analyze the first condition. If it is true, then the agent selects the related action. So if we don't have the ticket, the agent doesn't select it and not paid it, and there is no error, the agent can select the ticket. If the atomic proposition selected is true, so this means that the agent already selected the ticket, then it can pay. Otherwise, in all the other cases, he can do idle. Given this strategy, we can determine also the related complexity. For the number of atomic propositions, we have 4 atomic propositions: ticket, selected, pay, and error. For the largest condition, we need to count every symbol of the first condition, 11. And for the total set of the representation, we just need to sum the different conditions, so 11, 12, 13.
Did you assume some normal form for your conditions?
No, there is no definition for normal form, but okay, from a theoretical perspective, I don't think this changes something. However, for the implementation point of view, Obviously, we try to construct the strategy with the less complexity as possible.
So you could factorize the
Yeah. Yeah. From the implementation side, yeah, we have used this kind of approaches. Yeah. But from the theoretical perspective, yeah, it doesn't have an impact on the complexity class. And given this new notion of strategies, we have introduced a variant of ATL that we call the NAT ATL, in which we can check whether there exists a natural strategy with a given complexity to satisfy a temporal objective. Given this new logic, we have also analyzed the model checking complexity. In this case, the parameters are again the memory of the strategies and also the bound K related to the complexity of the strategy. And in particular, if K is fixed, so it's not a parameter of the problem, the complexity of the model checking is polynomial for memoryless strategies, and it's in the polynomial hierarchy with the strategies with memory. While if K is a parameter of the problem, for memoryless, again, we are in the polynomial hierarchy. I remember you, this means we have an oracle that guesses a strategy, and then we have a polynomial time algorithm. While in the worst case, K parameter of the problem and strategies with memory, the problem is P-space. The good news is the fact that these results hold for both perfect and imperfect information. And this is a good result for the imperfect information part, because as I told you before, for strategies with memory, we have an undecidable problem in general. So we have defined a way to make this context tractable. For the specification part, we have introduced a new logic that is called abstraction logic that for the first time introduce a way to use temporal logics with the dynamic modeling. With the dynamic modeling, I mean models that can change along the execution of our system. In particular, we have defined a new model in which for every age, we have assigned a cost, and this cost is fundamental for the possible ages that can be eliminated via obstruction agents. We have also slightly changed the notion of strategy. Instead of having as codomain actions, now we have possible table of actions that represent the possible edges that can be eliminated in a specific state. Given this definition of strategy, we have defined also the semantics of this new operator to check whether there exists a demonic strategy, so a strategy that can eliminate edges, to achieve a temporal objective. This logic is very important to represent cybersecurity goals, in which we want to represent dynamic strategies for defenders and apply, for example, moving target defense strategies. Because in this way, we can eliminate some edges, so some possible attacks from an attacker, and make the system safe. Also for this logic, we have analyzed the verification problem, and in particular, we have found a fixed point characterization for this logic and provided a polynomial time algorithm to solve the problem, so make it tractable in practice. For the verification part, as I mentioned before, we have some problems that are undecidable in general, and we have provided a procedure to make a fragment of an undecidable problem decidable. In particular, the problem is ATL with memoryful strategies and imperfect information, and we have defined a three-valued semantics. So instead of having only true and false, we have true, false, and undefined, and an abstraction refinement method that, starting from the current model with imperfect information, generates an abstract model with perfect information, and over this model, we verify the formula of interest given in input. If such a formula is true or false, so it's defined, we can propagate the verification result to the original model with imperfect information. While if the model checking result is undefined, the idea is to refine our model. The refinement is to select a state that can be splitted and can refine the verification of the atomic propositions involved in the original model. Over this new refinement model, we again check whether the property is defined or not. If it's defined, so true or false, we can propagate the verification result to the original model. Otherwise, we need to do another refinement step. As you can imagine, this algorithm is not complete because it's impossible. It's an undecidable problem in general, but we have identified a procedure that makes a fragment of this undecidable problem as decidable, and we provided a preservation result from abstract models to concrete models. So if something is true or false in the abstract model, we can propagate the verification result also in the original model. Last contribution is related to our tool Vitamin, that is a tool for the verification of multi-agent systems. The idea of this tool is to divide the different features and define also a hierarchy with respect to the different models and logics that we can take into account. Over this tool, we have a patent application for the software architecture and also a patent that has been published this year on a specific module related to a specific model and logic. We did this module with the company DEF. And the main idea is to define three main users. The first are classic users that want to verify models and specifications, and we have divided these users in expert and non-experts. For the experts, we ask the formal model and the formal specification, while for non-experts, the aim is to guide constructing the formal model and the formal specification of interest. Then we have in the middle the high-level developed part. In general, these are researchers that want to integrate new models and logics to our tool. Thanks to the modularity of the tool, we can add other modules without modifying the core engine of the tool. And then at the end, we have in the low-level part, low-level developers that in particular work on the optimization techniques to reduce the execution time of the tool, like introducing symbolic model checking techniques, BDDs, and also the abstraction refinement methods that we have already proposed in theory. To go deeper in the hierarchy that we have defined for the three steps of the verification process, for the modeling, the specification, and the verification part, we have defined the three different hierarchy. Each of them is related to the monolithic and multi-agent system part, and for every subtree, we have the different representation to this kind of systems. For the specification part, the first part of the hierarchy is related to the temporal and the strategic part. And for each of them, we have the related logics to the temporal part related to linear and branching time temporal logics, and the strategic logics that we have discussed, and also their related extensions. Because, for example, for alternating time temporal logic, we have a lot of extension for quantitative and qualitative representation of different properties. And for the verification part, again, we have for every module the verification algorithm related to a specific module for the modeling and the specification part. To well understand the machinery and the relation between these three hierarchies, we can see the verification flow for the tool, and in particular, yeah, as I told you before, we have two different interfaces for experts and non-expert users. For experts, we ask a formal model in a text file and a formula in a text box, while for non-expert users, we have for the modeling part an AI-guided modeling. So the idea is to interact with an AI and generate the formal model of interest, given the specification from the user. And for the formula part, the idea is to use natural language processing. This technique has already been defined for temporal logics. The idea is to extend it to logics for the strategic reasoning. The main challenge is to determine when we talk about of strategy and when we talk about of objective. And the NLP needs to identify this difference in the natural language process. Then, given the two inputs, we need to parse them, and the tool, given the model and the logic under exam, selects the right verification approach and provide the outcome. So this concludes the related part for our main contributions. I would like to conclude with some future directions, and in particular, also the lines that are related to some of our projects. For natural strategies, we have recruited a new postdoc, and we are working with him on developing the synthesis part of natural strategies, because the model checking tells us if there exists a strategy, but there is no way to synthesize the strategy. So there are some problems in which we want the strategy to achieve the objective. Then we are also working with the two PhD students on the cybersecurity field related to abstraction logics, and the idea is to apply them in autonomous vehicles and to also define new properties on the elimination part, because for the time being, the idea is to eliminate the edges temporary, but sometimes also defenders wants to eliminate permanently some edges. There are also other lines related to the expressivity of current logics, and for example, we are introducing the concept of nudging, also the bias part, and also ethics with respect to the different agents. These are related to norms. We are also working on introducing strategic reasoning in runtime verification. As you know, runtime verification wants to, thanks to a monitor, wants to validate an LTL formula during the execution of the system. And our idea is to introduce in this context also imperfect information of the monitors, and also the notion of rationality. This can have a strong impact on IoT systems. We are also working on smart contract verification, and in particular, we have defined a new logic to represent the liquidity property. The liquidity property means that in every step of the smart contract related to a blockchain, we need to guarantee that if an agent can ask to a refund, we need to be able to do this. And also there are several lines related to vitamin that we want to achieve. As I told you before, we have the objective to introduce AI in our tool related to two main parts. One is related to the interface, and I have already mentioned this part, but we want also to add AI to optimize the verification process. As you have noticed, there are several parts in which the model checking problem is in the polynomial hierarchy, and we need to guess a strategy. And the idea is to use AI to guess the right combination and make the execution time of the algorithm tractable in practice without having an oracle that needs to consider all the possible combinations of a problem. And we are also developing new methodologies to reduce the execution time complexity by using symbolic and abstraction methods. And also we are working with the new engineer of the team to some software engineering part of our tool. That's all. Thank you for the attention.